All right, it is 12 o'clock and time to begin our webinar. Thank you for joining us today for To the Core, Discovering Antarctica's Past to Predict Our Coastal Future. I'm Sam Glazer-Houston with the University of Minnesota Alumni Association, and I'm so excited to welcome you all to this shared space today. I'll begin with a couple of housekeeping notes. This session will be recorded today, and it will be then emailed out to everyone who RSVP'd, as well as uploaded to our Goldmine platform on the Alumni Association website so that folks can continue to access it. We also will ask you in that follow-up email to complete our evaluation. We do appreciate feedback about this webinar series and especially are interested in learning more about the topics you'd like to see in the future. And throughout the lecture today, you're welcome to submit your questions directly in Zoom. There should be a chat or Q&A feature that you can place your questions into, and then I will add them to a document so that they can be answered during our Q&A portion of the call. We also want to remind folks, membership powers everything we do. This webinar is made possible by the members of the Alumni Association. We want to thank our members and welcome everyone today who is a member or not, but thank you to those who are for making this possible. And we want to do a quick plug here for the Minnesota Travel Program. The Minnesota Alumni Travel Program offers alumni and friends a uniquely enriching way to explore the world through a curated selection of group tours focused on educational discovery and our University of Minnesota community. More than 800 individuals visit over 45 destinations with us across the globe each year, including an upcoming tour to Antarctica that Dr. Neff will be hosting. We'd love for you to join us on an adventure in the future, and to learn more about our travel program and upcoming tours, visit umnalumni.org/travel. I'm so excited to introduce someone special today that will provide our introduction to Dr. Neff, and that is Dr. Stanley Chernikoff. We are so lucky to have him here. Stan Chernikoff has brought geology alive to roughly 45,000 bright and curious students during his 35-year teaching career. And that teaching career spans both the University of Washington and right here at the University of Minnesota as well. Along the way, Stan also served as an assistant dean in the Office of Undergraduate Education and also spent 7 years as an associate athletic director, overseeing the academic lives of over 750 student athletes. Stan was also the recipient of the University of Washington's Distinguished Teaching Award in the year 2000, and in 2005, the James Close Award for the enhancement of academic communities on campus. Stan is a University of Minnesota trained glacial geomorphologist, getting his PhD here at the U in 1980, and has been studying geology of the Pacific Northwest since he arrived in Seattle in 1980. He's deeply committed to sharing his knowledge of the Northwest's ever-present geological dangers with his Seattle neighbors so that they might both appreciate and prepare for the myriad of geological hazards in this corner of the continent. Stan's also the author of a pathful of college-level geology textbooks that have introduced the wonders of physical and historical geology to a generation of American college students across the nation. These two folks share an incredibly special connection, and I'm so excited to welcome Stan to provide an introduction today. Over to you, Stan. Oh, do you mind unmuting yourself quickly?
There you go.
Should be good. Okay, this is such a pleasure for me for reasons that will become clear in a moment. A few brief words about my history. Yes, I did get my PhD at the University of Minnesota. I learned how to teach there in Smith Hall. I learned how to TA in Ford Hall. I have an enormous connection to the University of Minnesota. I was a glacial geomorphologist there, and I studied the ice dynamics that are largely responsible for creating the landscape of the Twin Cities, the glacial landscape. So the origin of the lands of Washington County and Ramsey County and Hennepin County and Chisago County were all places that I studied over my 7 years working there and teaching there, all the way up to Grantsburg, Wisconsin, in fact. I spent those 7 years in amazingly beautiful Pillsbury Hall. I was heartbroken when the geology department handed that over to English, but I must admit grudgingly that the renovation is incredible and spectacular. And I've been back many times for lectures in that building, just for nostalgia's sake. Another word before I move on to introduce Peter is that my wife, Julie Stein, also got her PhD in 1980 at the University of Minnesota and has had an incredible career at the University of Washington as well. As the director of our museum, she was also a director at the Bell Museum. So the connection between Washington and Minnesota is very strong. And in fact, I have to show you this. This sweatshirt that I am wearing is a kind of a conflation of Washington and Minnesota. I don't know if you can see it. I hope you can. But my wife and I are about to celebrate our 50th anniversary. We met and courted in Pillsbury Hall and in Memorial Stadium, where we were season ticket holders for Gopher football. And our big anniversary party will include, and I hope you can see this. Say yes if you can.
Yes.
Yes. A 7-foot-tall Goldie Gopher will be at our anniversary as well. So the connection to Minnesota is powerful. That connection is embodied by Peter in many ways, the Minnesota-Washington connection. He's the host for today's webinar, but I knew him when he was probably 18 years old when he wandered into my geology class, perhaps 20 years ago, maybe even a little later, a little longer, and proceeded to become one of the brightest and most capable students I've had over my 45-year history of teaching. And it's been an ongoing process. When Peter became interested in glaciers and ice, as he will teach you, I was a person who he came to talk to about that. So I get to have this incredible feeling of pride, almost parental kind of pride, to have watched his career develop and blossom as one of the country's leaders in determining past climate change through the record that's recorded in the Antarctic ice sheet. I was even more excited when he came after he'd gotten his master's degree and was working on his PhD to inform me that he and his wife Heidi had accepted positions at the University of Minnesota. So therein lies this connection between our two elite universities, embodied with Peter, and I guess historically with myself as well, because there's this history that goes back to my degree in 1980. Peter, as a geologist, does what I've been offered the opportunity to do, but have declined time and again, because he's more willing to brave the conditions of the South Pole than I was. It takes a special kind of geologist to be that uncomfortable in order to capture knowledge that is so crucial today. If you look at his mustache in this picture, you get a sense for what he goes through. Captured in the ice in Antarctica, which hasn't melted for many, many millions of years, is the chemistry of the atmosphere, which in turn tells us about climate. And Peter's work, even more crucial today, involves the effect of sea level change as the climate changes. So for those of you who are sitting in mid-continent, if you're living in Minnesota now, this is really fascinating stuff, but it's less critical than it is here in Seattle, because my house is less than 200 feet above sea level, and the possibility of sea level rising and encroaching on Seattle is a very real prospect. 3.5 billion people on this planet live within 50 kilometers of an ocean. So think in terms of the work that Peter's doing, while incredible and exciting and valuable in a scientific way, helps us to prepare for the inevitable, that the seas will rise. And if you vacation or you have winter homes in Florida, be talking to a real estate agent, be thinking about whether that land is safe over the next 15 or 20 years, because seas are rising and that will have an impact. And Peter's work will inform us about this. So I'd like to hand this off to Peter, and I can sit back and just feel a sense of pride of a parent watching his academic offspring save the world in many ways. So, Peter, how do you like that?
Thanks, Stan. Thanks
Take it
so much.
away. Thank you for
Yeah,
the work that you do. Thank you for your service.
thank you. Thank you for an incredible career as an educator and a mentor that's, gotten so many of us on to achieve things that we didn't think we otherwise would be able to. So I'll share my screen here if Sam, you're able to stop share, okay? And we'll just get things set up here. And of course, scientist that I am, I have far more information probably that I want to convey than I'm going to have time to. Stan, are you just seeing my slides? Does that look good?
They look good.
Awesome. Um, so I'll try to stay focused today and on time. We've got about 25 minutes or so before Sam starts to pull me off the stage here. But I want to share with you the work that I've been doing most recently in Antarctica in a really amazing sort of my scientific dream level of collaboration with colleagues in South Korea to get out to one of the hardest to reach but most important parts of Antarctica, and where we call West Antarctica, the very southern end of the Pacific Ocean. So I'm Peter Neff. I'm coming to you from Borlaug Hall over on the St. Paul campus, the farm, where the Department of Soil, Water, and Climate is, and the College of Food, Ag, and Natural Resource Sciences. So, here climate is central to so much of the work that we all do, and so much of what we rely on in this sort of stable climate where humans' civilization has developed over the last 10,000 years, and we've accomplished all that we have, and now gotten ourselves into all sorts of fun problems that we're trying to anticipate the effects of going forward in a warming world. So I'll try to leave you with some points up front in the inevitable case that I don't make it through all my information. So what we did most recently is on this Minnesota-led collaboration with South Korean colleagues. We went to Antarctica to get the first full 20th century record of climate near Antarctica's most remote and vulnerable glacier, a place called Thwaites Glacier. You might have heard about it in the news, called the Doomsday Glacier. A bit of an annoying term if you're a scientist that doesn't like flashy headlines, but it is a pretty consequential glacier. And we have no modern climate observations, no research stations anywhere near this place. So reconstructions of past climate are all we have to work with. And thankfully, Antarctica is the best place in the world to reconstruct past climate because of how cold it is, preserves all of the snow that falls, and we can use Antarctic ice cores to get high fidelity records of past climate, including samples of the past atmosphere. So I have, a little ice core here. Bubbles in the Antarctic ice are direct samples of the past atmosphere. So it's great that we can have such good records from Antarctica. Antarctica might seem really far away and remote from all of us, especially if you're in Minnesota at the headwaters, near the headwaters of the Mississippi River, but water does flow down to the ocean, and Minnesotans and our economy does rely on coastal infrastructure and river infrastructure as well. So West Antarctica is really central to the uncertainty in our future sea level rise. And I've been sort of the one person and my team as part of the international ice core community that are trying to bring our tool, ice core reconstructions of past climate, to bear on this really critical question: how much sea level rise is going to come from Antarctica, and how fast? So we got a lot to cover. I'm sort of here, I guess, because I've been in actually both alumni magazines across these two amazing public institutions. So thanks to Chris Quirk, who put these together. And I think Stan might be one of the only people who have both of these in his inbox from UW and University of Minnesota. But the reason I share this is that I wouldn't be here without these fantastic public universities. So I'm so thrilled to be a professor at an amazing world-leading public university like the University of Minnesota, where folks from any town in Minnesota can end up here and potentially expand their opportunity and grow as citizens, of our country and also of the globe. So I feel really grateful to have had the opportunity, and I will add that I wouldn't be here without, in this position of leading Antarctic research project, without the public universities and our U.S. federal university partnership, which has been central to my experience as a member of a university community, a researcher, in addition to an educator. This is the 75th anniversary year of the National Science Foundation, which funds frighteningly close to 100% of ice core research in the United States. And it certainly has been the hardest year at the foundation ever. And I'll try to circle back to some thoughts on this, where we are in the year 2025 and where we might be headed. But I'm going to be challenged by time already. So here we go. So it's that university federal agency partnership that first got me to Antarctica. I don't know why I was looking so intense here, but this is something like 15 years ago, my first trip to Antarctica on the deepest U.S. ice core ever drilled, where we drilled more than 2 miles thick to the bottom of the ice sheet to get a 70,000 year long climate record. I've been very lucky to get a lot of opportunities to not just be in the classroom, but to be out on the landscape with people like Stan, and then out in the field, places like Greenland and Antarctica, becoming a field-based glaciologist and ice core scientist with that support from the National Science Foundation and the U.S. Antarctic program, which I'll talk a little bit more about in a minute here. All of my projects, and I've tried to splash the NSF logo here a lot, all of my work in the field has been supported by the National Science Foundation in some way, shape, or form. And it's gotten me from that very first trip to then leading my first project in Antarctica with my fantastic colleagues at the Korea Polar Research Institute, that we'll try to spend the last 10 minutes of the talk on or so, if I can keep to some semblance of time. So I want to go through Antarctic ice cores first before talking a little bit more about Antarctica and how we do research there, and then get into how I'm applying ice cores to coastal change in Antarctica. My pitch slide for ice cores is this. They allow us to explore climate processes, trends, extremes in places or at times where we don't otherwise have observation. So if we wish we set up a research station next to the most critical glacier in the world, we can wish all we want, but the only way we can go back in time is by drilling into the annual layers of snow and ice and building a record from the chemistry in that snow and ice. Those records give us perspective on climate, environmental, glacier, and ice sheet sensitivity in a warming world. So we can get a lot of different Earth system processes through that sensitivity term, where we're trying to replicate some version of a high fidelity past observation. And that observation then can become a test for things like our glacier ice flow models. But without observations of past states, we don't have things to test our models. So ice cores are a really important observational tool, even though we do have to do some forensics to sort of reconstruct our past climate. So very simply, to try to move through ice cores 101 here, snow attaches itself to chemical impurities in the atmosphere. And so as it falls in Antarctica or on any glacier, the changes in those chemical impurities in the snow layers tracks environmental processes. As you pile up something like 100 meters of snow, you're compressing that snow and that pile of snowflakes into solid ice that traps air, those isolating bubbles of the past atmosphere, which in Antarctica are our only record of past carbon dioxide, the most important greenhouse gas in the atmosphere. So all of our ice core drills roughly look the same. They vary in size based on the depth you're going to or how much sample you need. These are actually the biggest, fattest ice cores we drill, but in general, we're drilling 1 to 2 meters of ice at a time, popping it out, and then we have a sequential core going back through time where we can measure the chemistry of the layers of those ice. So don't get too worried about any individual track there. I've labeled a few, but the annual chemistry variation in ice core samples allows us to count layers back in time, and then also calculate the year-to-year environmental variability from those records, like sulfur variability related to sea ice conditions in Antarctica. Once we have a core, we have to get it to the lab. Ice cores are sort of funny. There's nothing to do with them in the field. You can't see anything in them. We have to take them to the lab where we actually melt them and plumb them into instruments to turn them into geochemical records of past environmental conditions. We've done this all over Antarctica, mostly in inland regions, because ice core scientists really like ice domes. We like our layers of ice to be most easily interpretable in a nice, essentially non-flowing stack where all of your ice accumulated right where the snow fell. And so we need to do that on top of ice domes. And we'll get to this in a bit, but my work is sort of pushing us out to the coast due to the unique fact about Antarctica that it's actually surrounded by little miniature ice sheets, miniature coastal ice rises, ice domes, that are our opportunity to get closer to these complex glaciers that are changing. in these challenging environments. So I've added my site there at the left on all of our sort of big, deep Antarctic ice cores. And so we'll get out there in a minute. So just to summarize what we do with Antarctic ice cores, they give us records of regional to global climate and environmental processes. So ice cores about Antarctic climate, but also ice cores with a clean archive of carbon dioxide, which is a globally well-mixed gas. So we can get globally relevant records from that. And those annual layers, we can count back for thousands of years, tens of thousands of years in some places, which then get us to having deep continuous ice cores that give us a continuous time series from today back, pushing back to 1.2 million years, actually, just right now. And then we also have some stranded ice in places that gets us snapshots back to 6 million years. And I don't have much time to show you this, but we have a paper coming out in the next few weeks from our NSF Coldex project, which is looking for deep ice core sites and also finding very, very old ice, 6 million year old ice, that actually takes advantage of an isotope of argon, argon-40, that was first explored by a guy named Al Nears in Tate Hall back in the 1940s, and we use as a geochemical clock for dating some of these very old samples. So just to wrap up ice cores quickly, I'll use an animation here that summarizes our history of CO2 that we have. So we started making modern observations in the late 1950s of CO2, seeing it increase in the atmosphere due to our burning of fossil fuels. We can stitch that with the highest resolution ice cores to see how we've rapidly changed the atmosphere in the industrial period. And then by drilling these deep ice cores, we can go back in time 800,000 years, where we see 8 ice age cycles over that time. And we also see that our current level of CO2, this plot is now 5-6 years out of date, but obviously our current levels of greenhouse gas increase in the atmosphere are absolutely unprecedented and are what are leading to the globally average warming that is certainly not great if you're a glacier, and is not great for a whole lot of systems. And that's, the consequences of warming that we call climate change. But so let's, back up a little bit from ice cores and think about Antarctica for a second. So a little bit of Antarctica 101 and how we do research in Antarctica as Americans, and then get into Antarctica's role in our future sea level rise. So this is a map of Antarctica that we already looked at. We break down Antarctica into West Antarctica and East Antarctica. This map is the highest resolution digital elevation model for Antarctica, and it's actually in part created and hosted and updated here actually on the farm at St. Paul campus at the Polar Geospatial Center, which is an NSF center. Actually, I just had coffee with those folks this morning. They are leaders in geospatial support and provide that support for all NSF polar programs activities. We know that Antarctica is very consequential for sea level rise, in part because we've also mapped out ice thickness over the years. So it's 2 miles thick or more in some places. Antarctica is very large. It's about 8% of the global land surface. And because it's not just a thick continent with a thin veil of ice over it, it's the opposite. It's a big, thick pile of ice sitting on a continent and in part sitting below sea level. The volume of ice is equivalent to about 60 meters of sea level rise, or 170 feet of sea level rise. So glacial, interglacial cycles, Antarctica, Greenland, and the Northern Hemisphere ice sheets are throwing a lot of change at us, which are why they're so important to track going forward as the world continues to warm. We know about this ice thickness from airborne geophysical surveys that have been conducted since the 1960s. This is the most recent one that we led as the Center for Oldest Ice Exploration, flying a grid from South Pole Station that was close to the area of the state of Minnesota. Looking at those deep layers below, those are the layers of time preserved in the ice sheet, where we're actually looking for other deep drilling sites. So it's also new result just came out in Geophysical Research Letters just last week. And we pieced together all of these different projects to understand not only what Antarctica looks like from above, but what it looks like from within by sounding it with radar. And that allows us to calculate the volume of Antarctica and its impacts for sea level rise. Antarctic ice flow is much more complex when you actually start putting velocities on it. This is from NASA satellite observations showing how ice flow channelizes and forms these purple and red fast-flowing rivers of ice called ice streams that flow out to the ocean and drain the ice sheet. There's a Minnesota name on here. Rutford Ice Stream is named after Bob Rutford, who's an alum, did his PhD in the 1960s, actually mapping the mountain range right there by the Rutford Ice Stream, and a couple of Minnesota place names in there because of the couple of years of Minnesota field work early on in the U.S. Antarctic program in the 1960s. Minnesota Glacier, Gopher Glacier. I think there's Pillsbury Tower is out there. And Bob Rutford's also a St. Paul campus person. He grew up here in St. Anthony Park, and his dad actually led the extension program in the 1950s. So Antarctica works by piling up big stacks of ice, and it flows under the weight of gravity out to the ocean. So here's an above view and a side view of how one of the major outlet glaciers in West Antarctica works. So just to sort of get through this, snow's falling in, it piles up, flows out to the ocean. In Antarctica, the ice is not melting around the edge of the continent. It goes afloat in the ocean. And then tidal activity, storms break off icebergs. And the ocean actually is a primary driver of change of melt from below these ice shelves in Antarctica. So if your snow falling in equals your ice melting and flowing out, everything's good for the ice sheet. And unfortunately, that's not the case, and it's unlikely to be the case going forward. And I'll show you those observations in just a minute. So that's a little bit about Antarctica 101, but how do we know that? And how does somebody like me from anywhere USA or Brush Prairie USA, where I grew up, get to Antarctica with capacity, with funds remaining to actually do some science? And that's where our national investments come in. So the United States Antarctic Program is funded and operated under contract by the National Science Foundation. And since its inception in the 1950s, it's hard to get a concrete number, but we've all collectively invested somewhere between 10 and 20 billion dollars in this world-leading operation that's 10 times larger than any other national operation in Antarctica, and it has allowed us to establish a peaceful, long-lasting treaty system in Antarctica and lead on international collaboration in the name of science in Antarctica. And there's nothing that gets screaming eagles playing in my ears like talking about the U.S. Antarctic program. It's a really capable program that's supported by people and equipment and branches of the military all over the country. We got C-130s built in Georgia, Boeing's built in California. We use the Coast Guard cutter Polar Star that's home ported there in Seattle, where Stan is. And we've had two ice-breaking research vessels that are based out of Louisiana. All of these things come together to allow us to lead in our understanding of Antarctica and what it means for the rest of the world. Antarctica, what happens in Antarctica doesn't just stay there. So the program supports U.S. activities in Antarctica in sort of three ways, and I'll go step through them and get up to my bias, but also what the science community has identified as the top priority in all areas of Antarctic science. So we use Antarctica as an observing platform. South Pole Station in particular is a really good telescope location and space physics observatory. So we ask questions about the universe there. We use Antarctica as a place to understand its systems, its unique biota and processes. So how extreme environments affect biological communities is a really big line of questioning there. But then our top question across all scientific disciplines in Antarctica relates how Antarctica will contribute to our future of sea level rise. How much sea level rise will come our way? How fast? And I'm trying to apply ice core science to that question because I found it sort of odd that nobody in our community is trying to do that. So that's what we're trying to get to here, and we're already going to be struggling for time, I can tell. So the kicker of why that matters is if you start looking at projections of sea level rise that include all ice on Earth, Antarctica jumps out as the big outlier. So we have a range of choices of our futures. These different colored lines projecting out to the year 2100 are scenarios of our choices with respect to greenhouse gas emissions, heat trapping gases that are going to warm the world and melt ice and lead to global sea level rise. We sort of have a choice between a half meter or a meter of sea level rise by the end of the century, but there's this pesky dashed line at the top. That's our understanding about rapid behavior of the West Antarctic ice sheet relating to those outlet glaciers where I've been taking us to. So Stan and I as geologists are not too uncomfortable thinking about deeper time. Deep time for a normal human probably would be something like projecting out to the year 2300. And if we do that for sea level rise, the upper bounds on sea level coming from Antarctica get pretty uncomfortable. So by 2300, when I hope we still have a thriving global society, we can't rule out sea level rise greater than 15 meters, 45 feet, because of the behavior, the potential runaway retreat of West Antarctica. So our uncertainty and understanding of West Antarctica added to our range of choices in greenhouse gas emissions lead to this uncertainty of, are we going to have 1 meter of sea level rise in 250 years, or are we going to have 10 or 15 meters? That's a big difference. And this is not something we've just started to worry about. So this is a paper from 1979 in Nature, West Antarctic ice sheet and CO2 greenhouse effect, the threat of disaster, where this guy, James Mercer, was worrying about the collapse of West Antarctica there. You can see from left to right the difference in what the geography of Antarctica would look like. And that's what we're still looking at today. So here's a much more updated version of observations from NASA of this. So if we play the time series of, these are GRACE satellites, the satellites that are measuring the gravitational attraction of Earth. You can see that ice loss in Antarctica, the mass loss, this is measuring the change in mass of Antarctica, its gravitational effect on these satellites. It's almost entirely focused in coastal West Antarctica, and we can simplify that to that it's almost entirely focused at this one glacier, Thwaites Glacier, a Florida-sized glacier at the southern end of the Pacific Ocean. So unfortunately, thinking back to your Antarctica 101, the snowfall in is not equaling the ice flow out. So we need to understand what's going on at Thwaites Glacier. And that's where I come in, trying to give us better climate perspective on that place. So I know we're going to get tight on time here. So I'm going to step through some maps here pretty quick to think about this. So here's the star where Thwaites Glacier is with respect to our US infrastructure in Antarctica. Not exactly in an efficient location, more than 1,000 miles from our main hub at McMurdo Station. We add on all the other permanent research stations. You can see we have a coastal bias. We're humans. We don't live in Antarctica, so we have to approach it from the coast. And all of our research stations are largely remain at the coast. And we have a conspicuous gap in this place called West Antarctica, where we have no research stations and no long-term climate observations. And it's because it's a pretty stormy, pretty nasty place. The Southern Pacific Ocean is not a great place to be. It's not a small place either. So we have a West Coast sized coastline with no research stations and no long-term climate observations. And that's bugged me for quite a while now. So the little problem about this most important glacier in the world, it's 1,000 miles away from any research station and hard to get to. But that's where my objective study comes in. So ice rises are these essentially mini ice sheets that ring the Antarctic continent. They're a miniature version of the ice domes we like to drill deep ice cores on. And they're located right in the center of action where all of this change is happening in Antarctica. So if we can get out to those places and collect ice cores, it gives us a chance to reconstruct past climate along the least observed and fastest changing coastline of Antarctica. So we can add, don't worry about any of the red boxes here, but this glacier system is big. It's the size of a US state, and it's changing by minute by minute, hour by hour, year by year, and decade by decade. But ice cores can give us year by year time perspective on the processes, the winds, the temperature, the ocean currents that are pushing around this system. And we can get just 100-year-long records by drilling 150 meters deep, 300 feet deep. And that's as deep as we can drill relatively fast and light. And fast and light is sort of important because we need to get way out there. So great. I showed this picture of, this is our US icebreaker, Nathaniel B. Palmer. We can just use that. We can get out and go. But this ship has a problem that even though it has a heli deck, it's not had helicopters on it historically. It's not a cheap operation using helicopters on the ship. And there's some sort of disciplinary barriers there where the ship is used for marine science. But once you start to realize how important the ocean is for the ice, it's a little dissatisfying to go all the way there to just look at a place like Thwaites Glacier from the ship, but not be able to get out onto it to do any science on ice. And that's where my colleagues from the Korea Polar Research Institute came in and really have expanded our capabilities. So they were willing to try this, and we collected the first 150-meter deep Antarctic ice cores that were recovered entirely by an icebreaker with helicopters in sort of a sprint style of operation, which is really not how we do this sort of work in Antarctica. So I do have a little bit more, Sam, so if you just give me another 5 minutes here, I'll try to rush through. I'm skipping over a lot of details and years of back and forth and getting expeditions organized, but eventually in December 2023, we sailed the week or so from New Zealand to the Amundsen Sea, where Thwaites Glacier is, to get out to one of these ice rises and patiently wait. We're looking at our objective there on the right to fly off the ship and establish our camp. And getting the weather to align on any sort of elements to align in Antarctica is always a challenge. But we got very lucky in this case, came all that way. We're able to park up within 1 kilometer of our site of interest, and then use the helicopters to get an entire camp, 8 or 9 people in with 2 weeks of capability, 2 snow machines to do ground-based radar surveys. And we did this by doing 12 to 20 almost back and forth flights with 2 helicopters operating simultaneously. So this is what it looks like to leave the ship, and you'll quickly see why we need helicopters to safely get up onto these ice rises, which are they're essentially like pancakes of ice right out on beachfront property. So they're nice and flat, slow ice flow, no crevasses in the inland regions, but the edges of them, you have a severely crevassed region that you need to get over with helicopters. So we were able to set up our camp pretty quickly in just a matter of 4 to 6 hours. And we did it just in time because we knew a storm was coming that we needed to weather before we could get to work. And so this is what the storm looked like before it got bad. And you can't really see much, but we did just lose 1 or 2 tents, but nothing blew away. We didn't lose any equipment, and we hunkered down for 36 hours or so, enjoyed some hot beverages once we could dig ourselves out of our tents, and just waited to get to work. And so the nature of life in Antarctica is you're not in control of the weather, that is for sure. But once the weather clears, you're off to work. So this is what the light drilling operation looks like with the work that we do. This is equipment provided by the U.S. Ice Drilling Program, the National Science Foundation. Ice Drilling Program is based at the University of Wisconsin, another Midwest connection. And so this is a relatively light drill, but as light as we can go to drill the maximum depth before ice drilling gets really tricky and the ice gets high pressure. It's my PhD student, Julia, who recently graduated, and this was her first trip to Antarctica. So I'm going to move through this for time. Our drills are these cable suspended systems where we bring our coring barrel out of the drill. You'll see the inner barrel here, and we'll push out the ice core to then bag up and tag and bring back to the world for analysis. So this was really a unique sprint where we had less than 2 weeks on site, just 1 week of drilling, and we were still able to drill 2 150-meter deep ice cores, one with our US equipment and one with equipment that our Korean colleagues had. And as soon as we were done, we were then racing back to the ship, netting up our cargo and getting it on the ship, where it actually spent about 4 months on the ship before it finally got back. Our ice cores finally got back to South Korea and were unloaded at the Korea Polar Research Institute there. So again, the utility of helicopters on ships is essential and led to probably the best tagline that I'll ever have for my research, this daring James Bond mission to drill Antarctic ice cores. Very generous headline, but was satisfying to have that coverage. So in wrapping up here, I'll just say that our colleagues in Korea have been hard at work turning these blank ice samples, nothing much to look at, into our chemical records of environmental change near the most critical glacier in the world. This is the first time they've analyzed ice cores in South Korea. Their lab is fantastic. I visited in July, and we're trying to get continued funding set up. But of course, it's a challenging environment for that in the United States with the massive changes to the U.S. University federal relationship that I'll try to end on here. But I really could not give more kudos to my colleagues in South Korea for really leading, getting us to where we needed to go in Antarctica in a really, really, really challenging and new mode of logistics, and then also taking on the lion's share of actually processing the first round of cores in Korea. So Sam, I see you there. I'm going to try to get to my last point here and not dwell on these. I hope I got some sense across to you the importance of Antarctica with our future in a warming world with rising seas for the foreseeable future. I'm trying to get us an actual historic climate perspective on the most important glacier in the world, Thwaites Glacier. And thankfully, this big first challenge of actually collecting the first core out there was successful. The harder thing is the changing U.S. science funding landscape, where the proposed budgets coming out of the White House are lower than they've been in the last 25 years. Both chambers of Congress are trying to do a little bit better. It's unclear where things are going to end up. We've had decades of stagnant funding in the National Science Foundation, and that's having impacts in addition to the forward uncertainty. So the budget request was for 70% reduction in Antarctic research funding while keeping 100% of the logistical resources. Even in that budgetary setting, we've now lost both of our Antarctic research vessels in Antarctica, the Lawrence Gould, named after another influential Minnesota college personality, That ship actually just got back to Punta Arenas on its last journey and will no longer be a part of the Antarctic program. We have no U.S. Antarctic research vessels anymore. So, I don't want to end on a downer note here. So Sam's going to hook me off the stage here. But again, I wouldn't be here without the U.S. Federal University Partnership and our fantastic public universities. I could not be a bigger fan of how they get talented individuals out of their small locality into a big global world. And so we need to think about models going forward. Do we need new models for resourcing independent, curiosity-driven research and development at U.S. universities? Or do we need to recommit ourselves to taxpayer-funded U.S. science and redouble our efforts to justify it, to convey its value for all Americans? I don't know what the clear answer is here, but I know that global challenges remain, and we're really not doing enough to tackle them, particularly with climate change. I teach in the environmental science, policy, and management undergraduate major. Our students are not taught to ignore complex problems or leave them to other countries to deal with, and they're tired of waiting and ready to get to work. So, in the vein of our new way of thinking and our activities at the university, we need to keep moving forward, not wait for somebody else to pick things up. We have enough challenges out there to deal with. So I've been very lucky to have the support of the university and the National Science Foundation and my colleagues in Korea in exploring this work and expanding our understanding of how Antarctica is going to impact all of our future. So Sam, I've used up all of my time and more, but thank you all very much for your attention, and happy to take questions.
Well, thank you so much, Dr. Neff. I feel like I got a half a semester long course in 30 minutes somehow. So thank you for leveraging the time that you did have in the way you did. We have had a couple of questions come in, and you made a couple of different really important points here. So I want to make sure we get to at least these two questions. The first one might be a little easier, and I might say it wrong. Why is the Thwaites iceberg the most critical, and why is it melting and reducing the fastest?
Yeah, that's a great question. It's the most critical because it's a very big reservoir of ice. It alone, for the next century or so, contains enough ice that it could raise sea level by something like 10 feet. And unfortunately, because of the way glaciers carve out troughs, just like across Minnesota, we have evidence in some of the river valleys of glaciers carving out that terrain. The glacier has carved out a trough in front of it, so a sort of relatively deep, warm water body can get up on the Antarctic continental shelf and lap its way all the way under the floating ice shelf and melt it from below. So it's this really uh, unlucky situation where this warm water body has access to the glacier, and it's just this point focus of change in Antarctica. And yeah, unluckily, it's the furthest from any of our research stations in a really stormy, icy place. And we've been throwing a lot of resources at it, but again, it's embarrassing that the U.S. Antarctic program is in a place where we have no options to get scientists out to Thwaites Glacier for the foreseeable future. We have no resources to fly them out there. Everything's in sort of a rebuild and sort of complete previously obligated projects situation in Antarctica. So like we would have had something like 80 to 90 projects active in Antarctica this season, and everything got canceled down to about 30 projects this season. So those 30 projects are still really important. One of them is our NSF Coldex project. Only half of our work was canceled, but it's a challenge, and I love all of my colleagues at the National Science Foundation. They're doing as much as they can with limited resources and a lot of uncertainty. But yeah, Thwaites is in a really unlucky place.
And that actually leads into our second question really well, which is kind of about the funding piece here. So if public universities, as well as the National Science Foundation, are not able to keep funding this important research, are there private investors who would step in, or would this work stop? And what are those implications?
Yeah, I think we're becoming more and more familiar with the, thinking of the resources of individuals and, extremely wealthy billionaires who could put some resources behind this. But again, the annual investment that we are all making currently in Antarctica, just the logistical operation down there is $400 million a year. That's money spent in the United States as well. I think the way that we conceptualize federal funding can get a little bit wonky, right? You know, all of the funding that comes to the university comes, you know, we're spending out to other companies, operators, you know, FedEx, Delta, you know, equipment makers, and it's going into the U.S. economy. So, you know, I don't see individuals out there who are going to be able to make the sustained investment to have a presence like the U.S. does down there. And again, there are broader underlying motivations for having a sustained and capable presence in Antarctica, and that's for maintaining the Antarctic Treaty System that the United States was a major initiator of back in the late 1950s and early 60s when that treaty was put in place. To, you know, literally it's in the document to freeze territorial claims and conflicts that were beginning to emerge in Antarctica even before the Second World War. And preserve it for peace and science and understanding what it can provide us as far as understanding for the world. So, yeah, you know, that's part of my thinking of, you know, why could, you know, somebody from Brush Prairie, Washington have the opportunity to conduct science in Antarctica, and that's because many different nations now, you know, beyond the initial 12 signatories of the Antarctic Treaty System, recognize the value of investing in a national capability down there, so that our most creative folks with really relevant questions that we need answers for to you know, to help maintain a stable society, that we can get out there and ask and potentially answer those questions.
Wow. Well, this work truly is so important. I know that we have packed a lot in this hour and that you're actually off to a meet and greet now with some of our Antarctic trip participants for next year. And they'll get a firsthand look at the work that you're talking about. So we will wish you all a thank you. If the audience could join me in thanking Dr. Peter Neff for his time and expertise today, as well as his mentor, Dr. Stanley Chernikoff. Thank you both for your time today. Thank you to our audience. I will follow up with an email, as I mentioned, including an eval and a recording to today's lecture. So thank you all.
Great. Thank you, Sam. Thanks for being here, Stan. And if anybody wants to follow up on anything, I'm easily findable online.
Awesome. Thank you, everyone.